So now that we know what orthogonal matrices are, I want to introduce something called the singular value factorization. So this is a way you can take any matrix and write it as a product of an orthogonal matrix, a diagonal matrix, and another orthogonal matrix. So far we have, if Q is orthogonal, then Q inverse is equal to Q transpose. I think I've mentioned diagonal matrices before, but just to be sort of pedantic about it, I suppose. Diagonal matrix has non-zero entries, or entries that may or may not be zero, down the diagonal. So the diagonal elements are the elements where the two subscripts match. So it's the same row as it's in the same row as it is in column. So it would be D11, D22, D33, and anything where the subscripts don't match. So I is not equal to j. Those have to be zero. So a diagonal matrix sort of looks like this. It has non-zero entries down the main diagonal, and everywhere else it has to be zero. And if I have a diagonal matrix, this is also something that's very easy to compute the inverse of. So D inverse is just going to be the inverses of the diagonal elements. So I have 1 over D1, 1 over D2, and so on down to 1 over Dm. And so D inverse is only going to exist if all of these diagonal elements are non-zero. So orthogonal matrices and diagonal matrices have nice properties, so that in particular this one nice property, that they're both easy to invert. And so my idea is, wouldn't it be nice if any matrix could be expressed as a product of orthogonal matrices and diagonal matrices? And it turns out it can, and it's called a singular value factorization. So every m by n matrix A can be factored into, so U is an orthogonal matrix, sigma is a diagonal matrix, and V is an orthogonal matrix, and the factorization puts V transpose here. And so this is the picture for m greater than n. Really the only thing that changes, if the number of columns is greater than the number of rows, then this rectangle in the middle just turns sideways, so it's fatter than it is high. And then the V matrix, the V transpose matrix, so this star is the same thing as transpose. This would just be the bigger matrix, and U would be the smaller matrix, because the dimensions have to line up still. So I can take any rectangular matrix and factor it into an orthogonal factor, a diagonal factor, and another orthogonal factor. And so just a bit of terminology. So U is an m by m orthogonal matrix, and the columns are going to be called the left singular vectors of A. Sigma, so this is the matrix in the middle here, is an m by n diagonal matrix. So since I'm drawing the picture for m greater than n, so it's a matrix that has more rows than it has columns, the rectangle is skinnier than it is tall. And this dark band, this is meant to be, this is where the non-zero elements are allowed. And everywhere else in this matrix where it's white, those elements are forced to be zero. They're required to be zero. And so even though this matrix, just to make the dimensions work out, it has to have the same dimensions as the matrix A, it's only the elements where the indices, so the row index equals the column index, that are allowed to be non-zero. So you end up with this rectangular chunk of zeros in the bottom here too. And so this matrix contains something called the singular values of A. And so because the whole matrix is called sigma, the singular values are also denoted as sigmas. And they actually end up being in sorted order. So the top left one here, sigma 1, is the biggest. Then the one in the 2, 2 position here is sigma 2, and so on down to sigma n in the nn position here. And the singular values have to be greater than or equal to 0. And then finally, this matrix V on the right-hand side is a n by n orthogonal matrix whose columns contain the right singular vectors of A. And the motivation for this is that multiplying any vector that touches the unit circle, so this is a vector of length 1, so this set of vectors of length 1 is called the unit circle. When I multiply that by a 2 by 2 matrix, it's going to turn that unit circle into an ellipse. And so I've got this picture that everybody shows for this. And what ends up happening is you have these two directions that are kind of hidden. They depend on the matrix that I'm multiplying by. So in this case, my matrix A, it's got these right singular vectors, V1 and V2. And if you imagine what I'm going to do if I multiply A times X, what I'm really going to do with this is A times X is going to be equal to, if I were doing the multiplication stage-wise, I have to start on the right. So first I would multiply V transpose times X. Then I would multiply sigma times the result of that first multiplication. And then I would multiply U times the result of that second multiplication. So A times X is just going to be V transpose times X, then sigma times that, and then U times that. And what's going to happen is for these two special directions, V1 and V2, those are going to get rotated to be the new X and Y axis. So that's what the multiplication by V transpose does. Then when I multiply by sigma, that's just going to stretch this thing in the X and Y direction. So I'm going to stretch the Y values by a factor of sigma 2, and I'm going to stretch the X values by a factor of sigma 1. And then finally, when I multiply by U, it's going to rotate that, because an orthogonal matrix, you can think of it as a rotation, so it's going to rotate that back. And so what I end up with are V2 times, or A times V2 ends up becoming this vector here, and A times V1 ends up becoming this vector here. So I think I've done all of this down below. So I have A times V2 is going to be equal to my singular value factorization times of A times V2. Then when I do the first multiplication, so remember I'm doing this to one of the right singular vectors, V2. So when I multiply V2 by this matrix V transpose, I'll have V1 times V2, but because they're orthogonal, that's going to be 0. And then I have V2 times V2, and because these are orthonormal vectors, that is going to be equal to 1. Then I want to multiply this vector 0, 1 by this matrix sigma 1, sigma 2. And that's going to give me the vector 0, comma sigma 2. And then I'm going to multiply that by U. And so I'll have U1 times 0 plus U2 times sigma 2. And so that's sort of the story of how this vector V2 gets turned into this vector over here. So just to give another example, so it's kind of tricky to see what happens here because this only works for these singular vectors, because those are the ones that are going to end up being exactly on the axis again. So I end up with a vector either 1, 0 or 0, 1 when I have a singular vector. If I pick a vector that's not a singular vector, and then just define my matrices like this, so I made my matrix A just by choosing what I wanted its singular value factorization to be. So if I want to visualize this, I'll start out with choosing X just to be a vector that goes up 45 degrees and has length 1. And then I'm going to multiply that by V transpose. So V rotates a vector right by 22.5 degrees. V transpose will then just rotate it left by 22.5 degrees. So if I start out with this vector, multiplying it by V transpose, so I'm changing x here to be whatever V transpose times the original x was. That rotates this vector from here to the left until it's this direction. But notice it's still the same length. Then I'm going to multiply by sigma. So I'm going to stretch the x-coordinate. So I'll take this coordinate here and multiply that by 1.5 and stretch the y-coordinate by 2. So stretch the y-coordinate. So here, the y-coordinate is twice as high as it was over here, and the x-coordinate is 1.5 times what it was over here. And then finally, I'm going to multiply that by u. And so notice now this gray vector is just the product of a times x. Here, I rotated the vector. Once I've multiplied it by the singular values, notice it now has the same length as the vector that I'm aiming for. And then u rotates the vector right by 45 degrees, and that ends up putting it exactly over the gray vector. So that's just a kind of some idea of what this is trying to do, where the idea of a singular value decomposition came from. So the idea is you can think of matrix multiplication as a rotation, then some stretching, and the stretching happens in exactly the coordinate direction. So that's what makes it useful, is the coordinate directions are the easiest ones to work in. And then you have to rotate it back to get the answer in your original coordinate system. And so I made an example of this in R, and I think I didn't do this yet, but I'll put this data set on the course website so you can download this, and it's just these points here. And then there's a package called mass that has this function in it called EQSC plot. This just stands for equal scale plot. So all that's happening is whatever scale goes on the y-axis, exactly the same scale goes on the x-axis. So the y range and the x range are the same two numbers. Oops. And then I'm going to use a function in R. So usually a linear algebra class, they'd spend quite a lot of time explaining how you would actually compute a singular value decomposition. I'm just trying to explain a little bit of the interpretation. So R has a function that will compute it for you. It's called SVD. And I'm going to save the result of this function as something called SVDR. And this is actually a structure in R called a list. And you can get at the individual elements of those, so the pieces of the list, the things in the list, using the $ operator. And so the three things that the singular value factorization has are matrix U, the singular vectors, and the matrix V. And so I'm going to, in these next three steps here, oops. Okay, I guess I can't highlight them. I can do it that way. Okay. So these three steps, I'm just plucking out those things that I want from the SVD output. So the capital U will be the matrix U. Here, just to save storage space, if I have an answer that I know it's a diagonal matrix, usually R is not going to give me back a whole matrix that only has the diagonal that's non-zero. So what R actually does is just gives me a vector that's equal to the diagonal. So I'm going to use this function diag to make a diagonal matrix using the elements of that vector. So S here is going to be the matrix with these diagonal values. And then V is going to be the V. So it's not V transpose that comes out of the software. It's actually the matrix V. And then just to make sure I got everything right, this is just U times S, or this is the sigma part, and then times the transpose of V. And this function, all equal, returns true if it's two arguments. So this thing, which should all multiply together to be this original matrix, and the original matrix. So if those things are, if every element of those two matrices is equal, then all equal is going to return true. So this is just a little check to make sure that I did things right. And then what I want to do is look at what are the So V is the right singular vectors. So it's kind of hard to see because they're short here, but there's a red vector pointing up at about 45 degrees, and then this orange vector pointing down and right at about negative 45 degrees. And what I've done is just plotted, so arrows draws an arrow on a plot. So this is the red arrow goes from 0, 0, so it goes from the origin to the first singular vector. So that's just how you would draw the first singular vector. And the orange is the second singular vector. And so if you see what it's sort of showing, when I make the plot of this data set, it kind of has one long direction and one short direction. And so the right singular vectors are telling me what those directions are. So the first singular vector is pointing in the long direction. It also corresponds to the biggest singular value. And the orange arrow is pointing, what it's actually pointing in, here it's going to be the shortest direction, but it's pointing in the longest direction that's perpendicular to the first direction. So in a two-dimensional plot, there's only one direction perpendicular to the first direction. In 3 dimensions, if this were the first direction, then I could point any direction in the plane. So I would get the first direction being sort of the most variation in this cloud, the second direction being perpendicular to the first one, but then showing the second direction with the most variation, and then the third one being the smallest. So right now, this is just showing the interpretation of the right singular vectors. And now what I can do is also multiply them. I need to rescale. So they get bigger based on the number of data points I have. So I need to rescale the singular values by the square root of the number of data points minus 1. And now, not only does this plot tell you what the directions are, so the red direction is sort of the length of the most spread out the data can be. And it also gives you the relative length, so you can compare the length of the red arrow to the length of the orange arrow to kind of get some idea of the ratio of how things are spread out in the red direction versus how they're spread out in the orange direction.